Good afternoon. My name is Brian Jones, and welcome to an overview of the hydrogen economy. There's currently a major use of hydrogen worldwide, and at a value of $120 billion per annum, with annual growth of about 5%. So market demand is usually met by pyrolysis of hydrocarbons, such as methane, which unfortunately results in high levels of carbon dioxide emissions, which obviously are not environmentally friendly. Currently, about 2/3 of hydrogen is used for oil refining and also in fertilizer production. So for ammonia, for example, there's increasing demand because of more intensive farming techniques and also because of the increase in the world population. So the future demand is very much focused on green hydrogen. In other words, producing hydrogen in an environmentally friendly manner. So there's a major investment taking place in developing better techniques which are not harmful to the environment. There have been some very chilling comments made with respect to the issues mankind faces with respect to climate change. So, for example, Antonio Guterres, who's the UN Secretary General, has commented that every day I am faced with the challenges of a troubled and complex world, but none of them loom so large as climate change. Climate change is quite simply an existential threat for most life on the planet, including and especially the life of humankind. So if you look at global greenhouse gas emissions, there are a number of sectors which contribute very significantly to carbon emissions. It's not just carbon, there are other gases as well, such as methane, nitrous oxide, and ozone, which also contribute to the problem. So electricity is one of the biggest areas. So electricity currently is primarily produced by using fossil fuels. And the fossil fuels, of course, are oil, natural gas, and coal. Agriculture, then, is also a major source of emissions, and these arise from things such as livestock, such as cows, agricultural crops, and also rice production. And another key element is is industry as well, as you'd anticipate. So, for example, the steel industry worldwide is responsible for 7% of global gas emissions. Cement is also responsible for a further 7%. So industry in total, as you can see, is responsible for 21% of global emissions. Transport is one other area, hence the continuous focus these days on the use of electric cars to replace petrol and diesel cars. So those are the current means by which these global carbon dioxide emissions are generated, and there's obviously activity which you're already aware of in certain areas to try and reduce the greenhouse gas emissions that are generated. So if you look at global average temperatures from the year 2000 from the year 1000 to 2000, then up until the Industrial Revolution, about around 1800, for example, then there's a fairly static level of greenhouse gas emissions. And it's only since that time, with the Industrial Revolution, the wider use of electricity as well, that you see that temperatures have increased from roughly 13.7 degrees C worldwide to 14.3 degrees, a significant increase. And at the same time, there has been monitoring of carbon dioxide emissions, and as you can see, that's increased from roughly 280 parts per million in the world's atmosphere to around 380 parts per million. So the consequences of this are quite dire in many parts of the world because we're seeing more severe storms. Weekend before last, for example, we saw winds of 90 miles per hour in this region, which I can't remember happening for many years. In other parts of the world, such as in sub-Saharan Africa, there's been an increase in drought, for example, where many countries haven't seen rainfall for a number of years. And the consequence of this is there's an increase in poverty and displacement from agricultural areas to towns and large cities in sub-Saharan Africa. The warming rising ocean is also a major issue where melting of ice caps is causing this rise in sea levels, and consequently there are certain parts, certain islands in the Pacific which could be swamped in the near future. Bangladesh is a country as well where it's only marginally above sea level over most of the land territory. So lots of issues have been generated as a consequence of climate change, and therefore it's necessary for us to address that issue. So as a consequence of this increasing concern worldwide, there's been a lot of activity led by the United Nations, which led in the end to the Paris Agreement. Now, this is adopted by 196 countries worldwide and became live on the 12th of December 2015, where the goal was to limit climate temperature increases to 2 degrees centigrade in this century and achieve a climate neutral world by 2050. So not creating any more greenhouse gases than currently exist by using renewable energy sources, for example. So a key task, therefore, is to develop a rapid transition to low or zero energy carbon sources as a key to achieving this course and a maximum temperature increase of 2 degrees centigrade. This didn't happen overnight, by the way, the Paris Agreement. This was forged through decades of negotiations, but this was the first comprehensive climate treaty that was developed with the agreement of so many of the world's nations. And despite its many problems where countries haven't been meeting the agreed objectives, for example, it's still seen as a major breakthrough in humanity's effort to tackle the issue. Most experts are in agreement that it's helped to speed up action around the world, but the actions really haven't been big enough to date. And there have been a number of major warnings, not just from the UN, but from other authorities as well in recent times. The UK, for example, has pledged to cut back emissions by 68% by 2030 compared to levels in 1990. And our carbon footprint has fallen fast because so far by closing coal power plants and replacing them with renewable energy sources. So I've got an animation for us now to show some of these sort of types of hydrogen that are available.
When hydrogen burns, it generates energy in the form of heat, with water as a byproduct. That means energy created from hydrogen generates no atmosphere warming carbon dioxide, making it one of the many potential energy sources that could help reduce carbon emissions and slow global warming. But creating hydrogen and transforming it into a useful format requires energy, and that energy is not always necessarily renewable. That process is also inefficient and expensive compared with other forms of energy, renewable or otherwise. Producing hydrogen takes energy because hydrogen atoms don't exist on their own. They're almost always stuck to another atom, often another element. In the energy business, people generally refer to hydrogen by an array of colours as a shorthand for how it was created. Although this serves a purpose, it's not an ideal solution because it doesn't indicate how much carbon was produced in order to obtain the hydrogen. Firstly, green hydrogen is when the energy used to power electrolysis comes from renewable sources like wind, water or solar. Electrolysis is used to split the water into hydrogen and oxygen. Blue hydrogen is hydrogen produced from natural gas with a process of steam methane reforming, where natural gas is mixed with very hot steam and a catalyst. A chemical reaction occurs, creating hydrogen and carbon monoxide. Water is added to that mixture, turning the carbon monoxide into carbon dioxide and more hydrogen. If the carbon dioxide emissions are then captured and stored underground, then the process is considered carbon neutral, resulting in blue hydrogen. Grey hydrogen is made from natural gas, reforming in the same way as blue hydrogen, but without any efforts to capture the carbon dioxide byproducts. Pink hydrogen is made from electrolysis powered by nuclear energy, which does not produce any carbon dioxide emissions, although nuclear energy creates radioactive waste, which must be stored safely for thousands of years. Yellow hydrogen is hydrogen made with electrolysis from the energy grid. The carbon emissions vary greatly depending on the sources powering the grid. Finally, turquoise hydrogen is produced from methane pyrolysis, or splitting methane into hydrogen and solid carbon with heat in reactors and blast furnaces.
So there are a number of potential hydrogen production processes where hydrogen is seen as a complementary source of energy to renewable energy sources such as solar and wind. There have been projects, for example, aimed at improving biomass growth, harvesting and handling of biomass, reducing its cost. And those projects are ongoing. So while steam methane reforming is already carried out commercially, other processes such as thermochemical, water splitting, biological and photoelectrical chemical processes are in early stages of laboratory development and are considered potential pathways for the long term. However, the primary focus of research currently is on the use of electrolyser technology, which shows the most promise. So currently, almost all hydrogen for industrial processes is extracted from compounds. It isn't found in its pure form in general. So extracted hydrogen can be classified as three different products. You've got grey hydrogen, which encompasses more than 90%, 99%, I should say, of current worldwide production. And so there's a limited use of blue hydrogen, so that's produced by steam methane reforming, as mentioned in the animation, combined with carbon capture and storage. And there's green hydrogen. So as I mentioned in the last slide, green hydrogen is seen as the way forward for an environmentally friendly production process. But currently, production is only 0.03%. So the grey hydrogen is generally manufactured from steam methane reforming. So you've got natural gas, or ethane, butane, and light and heavy naphtha, for example, which is heated with steam at high temperatures and pressurized with a nickel-based catalyst to speed up the reaction. It forms both hydrogen and carbon monoxide as shown in that equation. It's an endothermic reaction, which of course, so the steam is providing the heat for that reaction to take place. So in addition to carbon monoxide generated, unfortunately, large volumes, as shown in the second equation, of carbon dioxide are formed as well. So for every kilogram of hydrogen that's produced, there are 10 kilograms of carbon dioxide. So grey hydrogen isn't the way forward in an ideal world. So I've now got an animation of the carbon capture process.
Carbon capture is one possible route to not only cleaner steelmaking, but also cleaner energy production. In fact, carbon capture is even being considered as a means of vacuum cleaning the broader atmosphere. Waste flue gases usually contain other gases besides carbon dioxide, such as hydrogen, carbon monoxide, nitrogen oxides, and methane. In a simple carbon capture technique, waste flue gases are intercepted before they exit to the atmosphere. Carbon dioxide is separated from other gases across a filter by spraying with a carbon scrubbing chemical, such as calcium carbonate. The scrubber binds with the carbon dioxide, which is restrained to the filter while the other gases are emitted. Under the application of heat and pressure, the scrubber is separated from the carbon dioxide. The scrubber is collected and can be reused. The carbon dioxide is collected and injected deep underground to be stored in porous rock, or can be used to make chemicals such as methanol by mixing with hydrogen.
So the other alternative is the focus of much research currently is green hydrogen by electrolysis. Now, electrolysis is the passing of a direct electric current through an electrolyte, which produces a chemical reaction at the electrodes, the anode and the cathode, and decomposition, in the case of water, into hydrogen and oxygen. So because of its environmental credentials, this is seen as the major process of interest going forward. So there's a need now to develop a system which is both economically viable and robust and capable of being scaled up from the low level of 0.03% of total demand at the moment to achieve a fully sustainable hydrogen economy. So, and this then, as I mentioned, is seen as the only viable option to achieve net zero carbon hydrogen production in 2050. So, so there is this need to develop this robust system, and there are two commercially developed processes at the moment. There's PEM, which is the polymer electrolytic membrane process, and alkaline electrolysis, and two laboratory-based systems which are only in the development stage at the moment. So there's SOEC, solid oxide electrolytic cells, and AEM, anion exchange membrane. So there will be competition between these four methods of developing green hydrogen. At the moment, it's unclear which will be the most successful by 2050. Nevertheless, PEM is the most attractive option at the moment. So obviously scale up is needed, but also there's a major degree of technical innovation required to improve the efficiency of these existing commercial systems, plus the laboratory-based systems to improve efficiency and the lifetime of the plants, because currently green hydrogen costs 2 to 3 times the cost of blue hydrogen. So I'll just show an animation of one of the commercial systems, the alkaline electrolyte.
Green hydrogen production involves electrolysis of water, the traditional method of which uses a liquid alkaline electrolyte. Two electrodes, typically fabricated from graphite, are placed in water. The electrodes are connected to a direct current DC power supply. The electrode connected to the negative terminal is called the cathode. The electrode connected to the positive terminal is called the anode. Electrons always carry a negative charge, denoted as E-. Electrons flow away from the anode to the positive terminal, attracted by the opposite charge. Electrons flow away from the negative terminal to the cathode, repelled by the same charge. Loss of electrons at the anode gives the anode a positive charge. Gain of electrons at the cathode gives the cathode a negative charge. An electric field is created in the water between the two electrodes, with flow of electrons from the negative cathode to the positive anode to complete the circuit. Electrical conductivity of water is increased by dissolving an alkaline electrolyte, such as sodium hydroxide, NaOH. This increases the rate of electron transport. Sodium hydroxide, NaOH, is an ionic compound with sodium, Na, carrying a positive charge, Na+, and hydroxide, OH, carrying a negative charge, OH-. The positively charged sodium ions flow towards the negatively charged cathode. The negatively charged hydroxide ions flow towards the positively charged anode. At the cathode, water gains electrons from the circuit to be reduced to hydrogen gas, H2, and hydroxide ions, OH-. At the anode, hydroxide ions lose electrons to the circuit to be oxidized to oxygen gas, O2, and water, H2O. The two half reactions combine to give dissociation of water, H2O, into hydrogen gas and oxygen gas. Evolved hydrogen and oxygen gases rise and are collected at the cathode and anode respectively. There is a negative cell potential for each half reaction and the combined reaction. The combined cell potential indicates the minimum voltage required to drive the reaction and thereby evolve hydrogen gas. If you are wondering why the positively charged sodium ions, Na+, do not gain electrons to be reduced to metallic sodium, that is because there is a greater, more negative cell potential for sodium reduction at minus 2.71 volts than for water reduction at minus 0.83 volts. Sodium reduction is therefore not electrochemically favourable and so does not happen, resulting in reduction of water and evolution of hydrogen gas.
So the system has been developed commercially, but nevertheless there are some drawbacks to the system. For example, the electrolytes, the potassium or sodium hydroxide can be corrosive, linked to disposal and potential leakage issues, and the reactions can lead to acidic carryover in the evolved gases, hydrogen and oxygen, leading to corrosion further down the line. It also occupies a large space. So, for example, a 100 megawatt alkaline electrolysis system requires an area of 15,000 square meters. And there are other disadvantages as well. For example, it needs a constant power supply. So if you look at renewable energy sources, which are essential to produce green hydrogen, then it can't work efficiently unless you've got a constant power. And you can't always guarantee a constant supply, obviously, from solar and wind energy. Also, the hydrogen has to be compressed then for efficient storage. The other, and currently considered to be the preferred system for hydrogen,
electrolysis of water using a solid state polymer electrolyte membrane, PEM, is the preferred method of green hydrogen production. The electrolyser cell consists of several key components. Firstly, two end plates, which are usually fabricated from titanium. The PEM is placed between the two end plates. The PEM is typically fabricated from a sulfonated tetrafluoroethylene-based polymer, which is solid material of 0.2 mm thickness. The PEM serves to carry protons from one electrode, namely the anode, to the other electrode, namely the cathode, and also to separate electrolysis products so to prevent recombination into water. The PEM is coated with a porous electrocatalytic layer on each side. Typically, carbon-platinum nanoparticles on the side that will become the cathode, and porous iridium on the side that will become the anode. The electrocatalytic layers are coated with porous current collectors. The space between each end plate and the current collector is filled with a porous gas distributor, fabricated from sintered titanium. Deionized water is then fed through one end plate via a series of channels on the side of the cell that will become the anode. The current collectors are connected to a direct current DC power supply. Remember that electrons always carry a negative charge, denoted by E-. Electrons flow away from the anode to the positive terminal of the power supply, attracted by its opposite charge. This draw of electrons from the anode gives rise to dissociation of the water molecule, specifically oxidation, with the water molecule breaking down into an oxygen atom, O, hydrogen protons, H+, and electrons, E-, and with the electrons lost to the circuit. Electrons flow away from the negative terminal of the power supply, repelled by the same charge, to the cathode. Loss of electrons at the anode gives the anode a positive charge. Gain of electrons at the cathode gives the cathode a negative charge. An electric field is created in the PEM between the two electrodes, with positively charged hydrogen protons, H+, flowing through the membrane attracted by the opposite charge of the negative cathode. At the cathode, hydrogen protons are reunited with the electrons from the circuit to be reduced to hydrogen gas, H2. The two half reactions combine to give dissociation of water into hydrogen gas and oxygen gas. Over subsequent electrolysis cycles, more oxygen atoms are produced, which then combine to produce oxygen molecules, O2.
There are drawbacks again with this system, in that whilst the method is efficient, the NAFLON membrane, for example, at the center of the cell, is highly acidic and equivalent to 10% or 10 to 20% of sulfuric acid. So it therefore limits the choice of a suitable catalyst, which is non-reactive, to the noble metals such as platinum and gold, for example. So expensive elements needed in construction make it more expensive than alkaline electrolysis, where these Naflon-based membranes that are commonly used in PM electrolysers are very expensive. There are also issues with water impurities, and the PM electrolyzer are very sensitive to this, which can cause a significant amount of corrosion. And also the lifetime of these systems, over a lifetime of say 10 to 20 years, hasn't been fully validated as yet. The iridium dioxide on the anode, for example, is prone to dissolution. That's a very expensive element. So there are these drawbacks, and so anodic dissolution of iridium oxide is of a particular concern. The next slide talks about the estimated crystal abundance of elements, and the cost currently of electrodes and diaphragms is a major issue associated with these two commercially available technologies. So to prevent critical materials from becoming a barrier to scaling up, alkaline systems, for example, need to transition from platinum and cobalt to cheaper designs using nickel, for example. And also world production of platinum is only 2,000 tons per annum. So if you're going up to the megawatt scale or terawatt scale, This will be a very significant problem because there just isn't enough titanium being mined annually. So for PM electrolysers, further efforts need to reduce the platinum and iridium content by at least one order of magnitude, and if possible, in the future replace them again with common materials, as will the alkaline electrolysers. So the strategy currently is to prevent or replace the use of critical materials with cheaper options, to increase the catalyst surface area, using nanostructured thin-film catalysts, for example, use thinner layers of coating material, and more efficient recycling of these elements, such as platinum, for example, and iridium. So those are some of the sort of targets that are required. And you can see from this graph that if you look at the abundance of platinum, 2,000 tons per annum currently, and significantly lower levels of sort of 40 tons of iridium currently worldwide. So this is a major concern going forward. So water electrolysis can be divided into three levels. There's a cell, that's the electrochemical cell, the stack, which is a combination of a series of these cells, and the system level then for activities which go beyond the actual electrolytic cell and the stack to methods then of processing the hydrogen. So the bottom section of this schematic shows the system level, the stack level, and that includes multiple cells which are now connected in series, as you can see, spacers, insulating materials between two opposite electrodes, seals and frames which provide mechanical support, and end plates to avoid leaks and collect fluids. In the top diagram, you can see that you need a renewable electricity supply, obviously, from solar and wind. This then goes through a transformer to increase the current, lower the voltage, and then a rectifier before the current is applied to the electrolyser stack. And then, as the process commences, of course, gas is separated in one direction, or oxygen, I say, is one direction, and hydrogen the other. And then that goes through a series of processes for compression and also collection and storage of the material. So power supply represents a significant cost component, typically 20 to 30% of the total. So there's scope there for reduction of the cost of electrolyser technology to make it more competitive with blue hydrogen, for example. So power system costs can decline through economies of scale and standardized designs and participation of specialized equipment suppliers instead of electrolyser manufacturers. So that is a key task. And in this respect, you'll be looking for leading manufacturers of electrical equipment who have extensive knowledge on improving efficiency of cost of power, can reduce the cost and increase the performance of the power supply for electrolysers, rather than using the electrolyser manufacturers to come up with a perfect pure supply solution. So the cost of water then purification is marginal because it obviously affects PM electrolysers and also to a certain extent alkaline electrolysers as well. So, but it's marginal. So even in areas where there's water scarcity, then it's possible to sort of quite cheaply to produce a deionized water supply, just satisfactory for the generation of green hydrogen. And for every 1 kilogram of hydrogen that's generated, you generally need 9 kilograms of water, as highlighted in the slide. Compression is a key aspect because hydrogen as an overall volume, low volumetric energy density, but a high mass density. So compression then is essential as an operation when storing hydrogen, for example. So large compressors are more efficient than small ones, obviously, and will result in a lower cost addition to the hydrogen produced. However, compression costs, as I mentioned, are relatively small anyway. So there are three potential ways to store gaseous hydrogen. So you can either liquefy the gas, where this involves cooling the gas down to minus 253 degrees centigrade. Unfortunately, that, however, requires a lot of energy. You can convert it into a liquid hydrogen carrier, such as ammonia, by combining with nitrogen, for example, where liquid ammonia is 19 times cheaper to produce than hydrogen, and boil-off rates are considerably higher during transportation, where liquid hydrogen, as I mentioned, has a storing temperature of minus 253 degrees C compared to minus 33 degrees centigrade for ammonia. So going from atmospheric pressure, for example, to 70 bar, a typical pressure for transmission pipelines, you can reduce the gas volume by 75, by a power of 75, by a factor of 75, I should say. So there is considerable interest locally in producing hydrogen economy. For example, many of you will be aware of the Highline project, where Wales and West Utilities have announced plans for a major hydrogen pipeline in South Wales to accelerate decarbonisation plans for industry and gas customers in the region. Highline Cymru will assess the feasibility of a pipeline network from Pembroke to the Swansea Bay Area, connecting low-carbon hydrogen production with industrial demand and providing options for other natural gas customers as well to produce hydrogen in place of natural gas. If the pipeline is built, then the pipeline will pave the way for commercial-scale hydrogen production in Pembrokeshire, Port Talbot and in the Celtic Sea, whilst also providing infrastructure for energy-intensive industrial customers to begin fuel switching their processes to hydrogen in the 2030s or earlier. It can also facilitate the conversion of home heating to hydrogen as well. So hydrogen storage and transport in gaseous form is preferred because hydrogen is in its natural state and it's a much cheaper option as well. And this graph illustrates, for example, that if you apply a pressure of up to 200 megapascals, then you can increase the density, the number of kilograms per meter cubed of hydrogen by a factor of 80. So this is the method which is widely preferred for transportation purposes. So there are a whole series of underground gas storage sites available. So, for example, natural gas is stored in underground sites currently. So existing man-made cavities from exhausted natural resources, for example, natural gas fields, oil fields, salt caverns, and coal mines are available, and these are now implemented currently on a daily basis. You also have man-made cavities. So you have to dig then to a depth of 100 to 150 meters in that case to develop the storage capability. That gas is stored in direct contact with the rock, and groundwater then exerts counter pressure to hold the gas inside the cavity. The alternative, as I mentioned, is liquid storage, and it does give you much higher volumetric energy density than gaseous, twice as much, 10 megajoules per litre compared to 5 megajoules per litre of 700 bar compressed hydrogen gas. However, the storage at very low temperature, as I mentioned, is the key issue. So it demands a lot of energy to liquefy it, and unfortunately, 30 to 40% of the energy of the stored hydrogen itself is required for this process. It also then demands more energy to maintain at a very low temperature, typically 1.2% of the energy in the stored hydrogen itself. The final option is to store it as a solid. So hydrogen may be stored in the solid state by binding with gaseous hydrogen with metals to form hydrides. The loading and unloading of hydrogen from the solid component is then activated by temperature and pressure. There is a penalty associated with this. Around 13% of the energy of the stored hydrogen is required for this operation. The product, however, is stable for storage at ambient temperature. But the high advantages, the good advantage is its high volumetric energy density, again, as in the liquid state. But the disadvantages are the high cost, high weight of the metal structure, and it's sensitive to wear over repeated loading and unloading cycles. So look at the summary of the current state of electrolyser technology. There isn't a single electrolyser technology that performs better for all applications. The future mix will depend on a lot of innovation and competition between these four technologies, for example, that I've already identified. So potential breakthroughs in technology then can be destructive, for example, in accelerating cost reduction in the SAC. For the balance of plant then, which is the system level, it's more about economies of scale, standardization of design and supply chains, and learning by doing. So building systems and evaluating their capability. Other technical challenges then include the lack of a hydrogen infrastructure currently, and energy losses at each stage of the value chain, and safety concerns over the high reactivity of hydrogen fuel, which could potentially lead to explosions, obviously. So the future electrolyser technology is to increase the capacity very significantly, to grow massively from 700 megawatts up to 4.5 terawatts by 2050 to decarbonize applications for which electrification is difficult. A terawatt, for example, is equivalent to 1 million megawatts. And the 4.5 terawatts we're talking about for 2050 would require 20,800 terawatt hours of electricity in 2050 if produced using renewable energy. Now that's equivalent to about 80% of global electricity generation today. But about 23% of the predicted 90,000 terawatt hours available for a net zero emission world energy system in 2050. Another factor then is also you need support from governments worldwide to invest in these technologies. So the other factors which benefit these systems, where green hydrogen could compete more efficiently with blue hydrogen, is the very significant decline in the cost of renewable energy from both solar and wind sources. So what we also then, of course, need these strategies to reduce the cost of electrolysers, as discussed in the last slide. So we look at the whole system that's planned for 2050. You've got the production processes, you've got renewable energy as a key element, electrolysis to produce green hydrogen, and without transformation, then you can ship it. Various transport systems are preferred. Pipelines, shipping, trucks, and you can store the hydrogen, which is a major plus compared to other renewable energy sources such as wind and solar. With transformation, you can combine with carbon dioxide to produce synthetic fuels, and combine with nitrogen to produce green ammonia, which is ideal for transportation purposes. And in terms of end-use applications, one can see there is significant interest currently in the steel industry, the chemical industry, and also in refineries. For transport, there's not a competition between electricity and produced from renewables and hydrogen, where in most cases electrification is the preferred option. Hydrogen has some potential also in heating and also in power generation. So hydrodesulfurization, as I mentioned, it is one area where it's used currently. So it's also called hydrocracking. It's a catalytic chemical process widely used to remove sulfur from natural gas and from refined petroleum products such as petrol, jet oil, diesel, and fuel oils. So the purpose is to remove the sulfur to reduce the sulfur dioxide emissions from using these fuels in automotive vehicles, trains, and ships, and so on. With the hydrogen sulfide then is subsequently converted into either solid sulfur or sulfuric acid, where the vast majority of such products are produced at refineries today. Total tonnage of 64 million tonnes per annum. Use of ammonia, as I mentioned, about 20% of total hydrogen production currently. So 80% of ammonia is used for fertilizers. It's also a common ingredient in household and industrial cleaning products, and in the production of plastics, synthetic fibres, dyes, explosives, and pharmaceuticals. For aviation and shipping, hydrogen now could make a very significant contribution in decarbonising the aviation sector. For commuter and regional aircraft, electricity may compete with hydrogen fuel cells. Unsustainable fuel or aviation fuels may also be used, which are produced from non-edible oil crops, such as camelina, municipal and industrial waste, flowering plants, and mangrove swamps. So for short and long-haul traffic, however, the majority is likely to be decarbonised not by electricity, but by sustainable aviation fuels, which are partly based on hydrogen, so it's a combination of the two, and potentially on direct hydrogen propulsion. Batteries are going to be far too heavy if you're flying from London to Sydney, for example. So in that case, the weight of the batteries makes it a huge disadvantage for electricity, and hydrogen will come into its own. So looking to the future, the EU Commission studies suggest that an efficient decarbonisation scenario will lead to 40% of all aircraft being powered by hydrogen by 2050, and the remainder by sustainable aviation fuels. Low carbon fuels are expected to be a major source of abatement as well for international shipping, along with other methods such as improved efficiency and electrification. Power then is another area where there is some potential application of for hydrogen, because of course the renewable energy sources such as solar and wind do not produce consistently throughout the 24 hours of a day, and at sometimes when the wind drops and when there's no sunshine, then there is a massive reduction in supply. So as a consequence of that, at points of low electricity demand, for example, low carbon electricity could be used to produce green hydrogen as a means of energy storage, an advantage they have compared to other renewable energy sources such as solar and wind power. So this could improve grid resilience by providing an important system balancing function, as well as improving energy security by diversifying the sources of power generation. Green hydrogen could play a strategic role in meeting these future power systems to provide medium and long-term energy storage. So that is a major advantages of the use of hydrogen. And then cement, the cement industry again is responsible for 7% of the world's carbon dioxide emissions, as I mentioned at the beginning. And for 1 ton of cement, you produce 1 ton of carbon dioxide. Currently, biomass is preferred as an alternative fuel, although green hydrogen may be of greater interest in the future as its cost reduces and there's an adequate infrastructure available, which obviously we don't have today. In the steel industry, there's a major push to replacing the current preferred option of the blast furnace and basic oxygen steelmaking route with electric arc furnace technology, where there are 2 benefits from the use of the electric arc furnace. It's a twofold improvement in that with the BF-BOS process, you're talking about 20 to 30% of scrap used at most, whereas with the electric arc furnace, you can use 100% scrap. It also has a major effect on carbon dioxide emissions. So you can reduce carbon dioxide emissions by 58%. It also reduces water use and water pollution by 76 compared to the blast furnace steelmaking route. And with electric arc furnace, you can switch it off. A facility is not available with the blast furnace process, where you would crack the lining and have to sort of totally replace it once a blast furnace cools down to room temperature. However, a key element of this, of course, is you need the electricity to be supplied by renewable energy sources. Otherwise, high levels of carbon dioxide emissions are transferred to the power plant. So scrap, and 100% scrap, is fine for many applications of steel products. However, if you're applying that steel to more demanding markets such as automotive and packaging applications, making tin cans, for example, then you will need to combine the scrap with direct reduced iron. So the Midrex process is one such process where the direct reduced iron is mixed with scrap to produce a product that satisfactorily meets the requirements of
Midrex is
more
the main
demanding.
gas-based shaft furnace process for producing direct reduced iron, DRI, accounting for around 76% of DRI production in 2019. Natural gas, composed mainly of methane, CH4, is burnt in air, oxygen, to produce hot reducing gases of hydrogen and carbon monoxide in the gas reformer. Iron ore in the form of hematite, Fe2O3, as pellets or lumps, is fed into the top of the shaft furnace. The hot reducing gases of hydrogen and carbon monoxide are blown in from mid-furnace. The hot reducing gases rise to the top of the shaft furnace as the iron ore descends. As the iron ore descends, it is reduced by the carbon monoxide from hematite, Fe2O3, to magnetite, Fe3O4, to wustite, FeO, and to metallic iron, Fe, all in the solid state, with carbon dioxide as a byproduct. And reduced from hematite to metallic iron by hydrogen with water as a byproduct. Waste flue gas, mainly carbon dioxide, as a byproduct of the reduction reactions by carbon monoxide, is recycled to the gas reformer. Once the process is up and running, hydrogen can be added to the gas reformer to reduce methane requirement. Then, carbon monoxide for iron ore reduction forms from the hot carbon dioxide emissions that are recycled. Efficiency of the Midrex process comes from the fact that methane is used for both heat and reduction. In the blast furnace process, and also the Corex process of DRI production, reduction comes from coke or coal, while heat comes from hot oxygen blasts. Moreover, hydrogen originating from methane permits some reduction without carbonaceous emissions. Finally, in common with the Corex process, carbon dioxide emissions are recycled for further reduction. As a result, the Midrex process can halve the carbon dioxide emissions from the blast furnace.
I haven't got time for this animation, unfortunately, but I'll
The
describe.
hybrid process is
I'll describe the process. The hybrid process, the acronym for Hydrogen Breakthrough Technology, consists of a consortium of SSAB, the major steelmaking company in Sweden, an iron ore mining company, and an energy company. So to use hydrogen as a means of reduction of iron ore to hydrogen in the Midrex process. To start off with renewable electricity, water electrolysis to produce green hydrogen, storage in its gaseous form, then application to the Midrex process, which generates then a carbon dioxide-free process for the manufacture of DRI. Then you combine that with scrap in the electric arc furnace, leading to a significantly reduced output of carbon dioxide emissions. So there is a concern with this. Unfortunately, there is a cost penalty associated with alternatives to the blast furnace process. So look at the bottom section here. There's a cost penalty, for example, for the use of hydrogen, which is expected to be about 30%. Now, will customers be willing to pay an extra 30% for a ton of steel, just because it's an environmentally friendly process? They may be forced that way in the long term, but at the moment it is obviously a stumbling block. The blast furnace BOSS process typically costs $395 per ton. Electric arc furnace process, $415 per ton. And electric arc furnace with direct reduced iron, such as the Midrex process, $435. So costs typically 10% more if you're developing steel for customers such as the automotive and tin can industry. So coming to a close of this presentation, now there are currently issues associated with the use of hydrogen. So the plans are now driven by climate ambition rather than immediate economic gain. Again, it's going to cost a lot more to use hydrogen than using the current processes, which produce significant quantities of unacceptable levels of greenhouse gases. There's interest in the use of green materials, but little demand exists at the moment. And there's also this lack of production infrastructure, so need to develop that infrastructure to increase demand. There's no hydrogen market currently beyond those, as I said, in ammonia and oil refining. However, a lot of companies are making efforts to develop improved solution, and this is being seen in the marketplace today. So the drivers for green hydrogen are lower solar and wind energy costs. They've dropped very dramatically. Many of the components required are ready for large-scale deployment with specialized companies, and hydrogen will enhance the flexibility of the power system because of the ability to store hydrogen very successfully. There are also government commitments worldwide to net zero emission goals, and there's an interest in multiple stakeholders, such as in the steel industry, chemical companies, ship owners, and airlines. So those are some of the elements which are driving the change. So if you look at the priorities now in terms of whether you go for electrification using renewable sources of energy, solar and wind, or if you go for hydrogen, then many of the needs in the future for carbon dioxide-free emissions are met by electrification. And hydrogen is seen as a complementary source in areas where electrification is difficult. So you can see for short-haul aviation, urban vehicles, electric vehicles are being encouraged by governments worldwide, trains, ferries, and trucks. Electrification is preferred. However, there's a sort of there's a changeover point where long-haul traffic, if you're driving from London to Poland, for example, then a long-haul truck, batteries will become very heavy, so hydrogen could then become more competitive. And there are major advantages for hydrogen in areas such as chemicals and refineries, as we mentioned, steel production, international shipping, and also for long-haul aviation. And the big plus, of course, seasonal storage. So the potential for the hydrogen economy is likely to play a key role in hard-to-abate sectors such as aviation and shipping, and in seasonal storage. And as a short-term measure, the use of carbon capture and storage is seen as an option to reduce greenhouse gas emissions from the primary means of hydrogen production today using steam methane reforming. So hydrogen and its derivatives can also be used to provide a cost-effective means for transport energy for long distances in pipelines, and as a means of conversion to chemicals such as reduced iron for steelmaking, which can then be transported to different parts of the world, which is easy to transport. So in conclusion, the reduced cost of renewable energy sources, combined with innovations which are anticipated in electrolyser technology, is anticipated to increase their competitiveness and the use of environmentally friendly green hydrogen. There are, however, major challenges which can't be ignored. To scale up the various competitive electrolyser technologies, where government support worldwide is essential to achieve the viable economic solutions which are necessary. So it's anticipated the demand for hydrogen will increase substantially in the future, primarily driven as a contribution to reach the net zero carbon emissions target set by the United Nations by 2050. So hydrogen will be needed for full decarbonization as a complementary source to electrification, offering a solution to heavy industry, long-haul transport, and seasonal storage.